Those of you who are paying attention may be wondering what this photo has to do with model-based testing. Well, I had planned to use a lame marketing line like, taking your testing efforts to new heights. But I really just like this photo. I'm John Wolfe with Maile Technical.
I am Alasdar Mullarney, also with Maile Technical. What we are presenting today originated a few years ago when John and I were modeling control systems for a high-altitude balloon project.
Okay, we know that most of us here really like building models of systems. But I wonder, does anybody actually enjoy testing them? Okay, well, I'll admit that I do actually enjoy engineering test suites. But then I also like to clarify and specify requirements, so there's that. Manual testing is tedious and error-prone, and it's really challenging to make manual tests repeatable. Certainly we can hand code target language tests, or we can use a specialized test scripting language. But I wonder, for us, perhaps there's a better way.
Of course. We pride ourselves on applying a model-based engineering approach to systems development. Why would we not do the same for test development? Note that we can build model-based tests in at least two quite different ways. So-called white box tests are directly coupled to the internals of the models under test, with the ability to manipulate those systems, creating instances, establishing association links, directing events to state machines, and directly interrogating attribute values. These tests are often useful in the early stages of modeling a system. However, tightly coupled to the internals of the models they are testing, they typically fall out of sync and either become a maintenance headache or more typically abandoned. Our focus here is on black box tests, which are coupled only to the interfaces surfaced by the models under test. Since these public interfaces tend to be more stable than the implementation details, these tests can be developed independently, and typically the effort to maintain them is much less.
Since the models we're building are platform independent, one of our goals for testing them is the ability to run in multiple execution environments while we're testing these models. One execution environment is an interpreter, bridgepoint verifier. This is where Alasdar and I do the vast majority of our test and debug work on models. It provides you with great visibility into all of the model constructs, including links between instances, the entire instance population, attribute values of each instance, as well as the current state of all active instances. You can also connect models executing inside verifier to external code. This makes it possible to do a great deal of functional testing before generating any code.
Another common testing platform is the development host. Once the models are running correctly in verifier, generating code to run on the host is a good next step. You can focus on sorting out toolchain issues while running a known test suite against application models that have already been debugged in verifier. This is often a more convenient environment to integrate code generated from your models with external code. And unlike an interpreter, execution speed in this environment is likely to be much closer to that of the target deployment.
In addition to running in multiple environments, we want each test to be repeatable so that we can track development progress and detect regression failures. Automating the execution of a test suite is one way to make each test reliably repeatable while eliminating the drudgery of manual testing. And while this goal may seem obvious, it's important that each of these tests issues a clear indication of whether it succeeded or failed.
So, model-based testing seems to have much to offer. But how do we handle interactions of these models under test with aspects of the system that do not yet exist, are not under our control, or are expensive or difficult to work with?
Well, unsurprisingly, we build more models. Specifically, we build a model test bench to simulate aspects of the system that the models we're testing must interact with. Each test bench is application specific and is focused on the needs of a particular project. For some systems, a really simple test bench is all that's required, while others may need a slightly more complex or elaborate test bench. Let's take a look at some of the types of things that a test bench needs to simulate. For many systems, the model test bench must simulate hardware components that may or may not yet exist. Things like sensors and actuators and mechanical systems can all be simulated by a model test bench, and this enables early testing of the software components that are being modeled independently of the hardware.
Other software components can also be modeled in a test bench, enabling parallel development of components or testing a new piece of software against a model of an existing one. Often it is useful to model the users of an interactive system. In some cases, it may even be necessary to model the environment in which the system operates.
In all these cases, the model test bench provides a substitute for aspects of the system that your models must interact with.
Modeling all these extra things sounds like an awful lot of work. Why can't we just test our application models in the context of the deployment target?
Well, we can, and eventually we will do just that. But in many cases, the additional effort required to build a model test bench pays huge dividends. In many cases, the decision about which bits of a system to model in your test bench is driven by several different considerations. Let's look at a few of those now. Access to an actual component, like a piece of hardware, is often a primary driver in this decision process. If the hardware doesn't exist yet, or it's particularly inconvenient to access, or it may be in very short supply, then it often makes sense to model it in a test bench. When we developed an autopilot for a stratospheric balloon, the actual vehicle hardware was in rather short supply, with only 1 or 2 vehicles in existence at any given time. And test flights were exceedingly rare, with only a few of those per year. In this case, it made a lot of sense for us to build a rudimentary behavioral model of the aspects of the vehicle that the autopilot would interact with.
Visibility and control of system components are a factor in deciding what to model in a test bench. Even when the deployment target is readily available, it may not be easy to understand exactly how your models interact with it. Test bench models give you excellent visibility into just how your modeled components interact with other components in the system. And some components of a system may be delicate and easily damaged when confronted by erratic control from an application that is yet to be debugged and verified to be operating correctly. Test bench models can give you the ability to control the environment in which your test models are operating. For an example, you might want to test over the full range of a sensor values, which may be virtually impossible with the real sensor. Modeled in a test bench, you can readily emulate the faulty behavior of sensors and actuators, enabling you to test and verify recovery paths within your application. During development of our balloon autopilot, a model test bench enabled us to fully test the behaviors of the autopilot independently of the test flight vehicle, which was being developed in parallel with the software effort.
Test bench models can be built at any level of fidelity and resolution that meets your testing requirements. Often, a simple behavioral model is all you need to verify that a model is working correctly. In other cases, for example, if you're trying to do performance analysis, you may need to build a higher fidelity, higher resolution model, maybe even a physics-based model, to interact with the models that you're trying to test. And often it makes sense to build a few different versions of a test bench for each project. For example, when you're running your models under test in Verifier or using generated code on your development host, the test bench needs to simulate everything in the system that cannot easily be connected to Verifier or the host executable. Running in the target deployment environment presents a number of interesting challenges and some opportunities. We typically recommend a phased approach for this type of testing. So start with a test bench that simulates everything that your models need to interact with. Since your application models and the test bench and the test suite have already been tested in Verifier and with generated code on the development host, the focus here is primarily on the target toolchain and the deployment execution environment. Then incrementally replace each simulated aspect in the test bench with the actual component being simulated. This allows you to focus your debugging effort on the interface between the models that you're testing and the actual component that you just swapped into place. Ultimately, a significant portion of the model test suite executes in the target environment without any simulated components or test bench required. Just keep in mind that some test cases, especially those that inject errors or manipulate the simulated hardware in ways that are difficult or impossible to do with the real hardware, cannot be supported in this particular environment.
We have used the term test suite a few times. What are we talking about? A test suite is a collection of related test cases where each test case corresponds to a particular scenario or use case. As a test case is executed, it injects stimuli and makes observations. Each observation compares the actual output to the expected output, and a mismatch generally results in termination of the test, reporting a specific failure. Each of our black box test cases orchestrates a series of interactions with the model under test, prodding it with interface messages, receiving interface messages from it, reacting to those received messages by either prodding it with further messages or by terminating the test. To be reported as successful, a test case must run to completion with all observations producing successful results.
Each test case runs unattended, so the entire test suite runs as a batch operation that produces a report indicating which tests succeeded and which ones failed. Whenever possible, we ensure that each test case can run using simulated time.
But I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts!
This ensures consistent results while minimizing the total execution time for the test suite. We often associate one or more requirements with each test case, allowing us to produce a requirements coverage report as a byproduct of running the test suite. Ideally, each test case would be expressed as a set of data so that we're not building a new state machine for each test. However, at this point, we do not have particularly good tools for managing pre-existing instance data. So we build models of stimuli, observations, and buckets of test cases, and we populate those models by executing action language. Since the test suite is application specific, we tend to package it in the same component with the test bench.
John and I now build our test benches with the aid of a modeled test framework, which had its roots in the Balloon project. Test framework. What might that be, you ask? Well, the simplest test we can conduct is to poke the system under test and observe what it does. In this context, by poking the system, I mean invoking a public interface to inject some stimulus, and by observing, I mean receiving some output, again through a public interface. However, all but the most basic of tests will have some notion of presenting a series of stimuli in some ordered fashion and observing a succession of responses. Add to that the notion of separating the stimuli in some timeline and perhaps attaching timeouts to some of the observations. I believe I see some application independence in those two sentences. While working on the Balloon project, I found myself needing to test a battery management model that I had been tasked with. Lithium-ion batteries are quite fickle and need careful monitoring. I was aware of the work John had done in building a test bench for the Balloon autopilot and looked to this for inspiration. John had established some interesting classes, the concept of a test suite organized into test buckets which sequenced related test cases. At some point, the abstraction I alluded to earlier became apparent. My test bench would be duplicating much of the work, sequencing stimuli, managing timeouts, collecting pass-fail data, and so on. As John knows, I had never quite abandoned my hacking predilections. I quite literally copied John's test bench into two new separate Bridgepoint projects and proceeded to hack the application-specific stuff out of one of them and the sequencing stuff out of the other. Thus was born the original application-independent test framework. As we developed test benches for other applications, we found the need to add capability. An observation, for instance, is associated with one stimulus. We need to see that the stimulus produces the correct response. But it may be that a stimulus produces several distinct responses. As a sensor notes entry of a vehicle into the car park, we may wish to note that the entry barrier has closed properly behind it, that the occupancy count has incremented, and maybe even the lot full sign is now illuminated. Many actions we observe are an immediate response to a stimulus, but not all. Hence, the framework evolved to handle polled observations, observations triggered by some later stimulus, and even concurrent observations which may rendezvous to complete a stimulus response. For example, our anachronistic car park accepts cash only. You insert your ticket, it displays the amount due, You insert bills and/or coins, and it spits out your validated ticket. But if you take too long to begin inserting coins or between coin insertions, the transaction is cancelled. So we may have multiple outstanding observations: ticket return, money dispensed, either change or a partial payment refund, and that possible cancellation, all hanging off that ticket insertion stimulus. In fact, it was that particular scenario that prompted support for concurrent observations. And who knows what enhancements may be supplied by future users in the xtUML community. In a test bench, a test case is represented by an OAL function that invokes create operations on application knowledgeable classes of stimuli and observations. These are subtypes of two supertypes, stimulus and observation, which know how to register with the test framework and know how to invoke callback functions. As test bench supertypes register, counterpart instances in the test framework construct the sequences that organize the test case. At execution time, the framework traverses these sequences, invoking callbacks to the test bench instances, which either inject stimuli or evaluate observation data. A stimulus completes when all its observations have reported a satisfactory completion via their supertypes to the test framework. If any fail, the test case is aborted. Otherwise, the next stimulus in the framework sequence is dequeued, signaling to its test bench counterpart to inject a further stimulus. The framework provides for tagging a test case with requirements identifiers, and thus can report on requirements coverage at the end of a test suite. I will just note that in two test benches we developed, one for the car park and another modeled payroll application, there is not a single state model. Stimuli are injected, observations evaluated. All the state-based sequencing happens in the framework. That, of course, is not always the case. The balloon autopilot required modeling the balloon dynamics in the test bench.
Okay, so there are several pieces to this model-based testing puzzle. First, there is an open source application-independent test framework. It's ready to use, so just go get it. Then for each project, you need to build a modeled test bench and a modeled test suite. These are both specific to your project, and they're driven by the requirements of your particular application. We typically build the test bench and the test suite incrementally, along with the application models. When we have enough of the application modeled to support an interesting use case or three, then we build enough test bench and enough test cases to illustrate those use cases. We test and debug the application models that are supporting those first few initial use cases, and at the same time we're testing the newly developed test bench and the test cases. As the application models grow in capabilities, we add test bench support for those new capabilities as well as test cases to exercise them. Of course, if you have more engineers to apply to the problem, then you can unleash several teams to work on these various pieces of the puzzle all in parallel. Like most test suites, modeled or otherwise, this one can be used for regression testing as the development and maintenance of the models under test proceeds. You can also measure coverage of this test suite, adding test cases as necessary to increase coverage.
If you have questions about model-based testing or want help in applying it to your project, do please contact us.